I'm in the process of trying to repair a vintage NCR computer. If you've watched the videos in this series so far, you'll know that I found a problem with the floppy drive interface. I've now got that working so we can boot from floppy disk, and I found various other problems with the main board. Got those sorted out, so the machine kind of boots up. The problem now is that I have actually got two of these machines to repair. They're not mine, they belong to somebody else. But I've got two to repair, a black and white one and a colour one, and both have faulty hard disk interface cards, and that's the card for this machine that's sitting underneath this tangle of wires. So as you can see, I've got these hooked up to the logic analyzer, and effectively what it does is we boot to the operating system using the floppy disk, but when we try and select the hard drive, it comes up with a message saying the drive's not ready, and basically that means it's not communicating with the host. So I've had a poke around with a scope just to try and see if there's anything obvious wrong with this. As I say, I've got two boards now. They've got different faults. One didn't allow the host to finish booting up. It put the welcome screen up for CPM and then it would just lock up, and that is because one of the custom devices on this board was asserting the wait signal, and that goes back and halts the processor on the main board, and that came down to one of the custom chips. If I swap the custom chip from the other board, it doesn't lock up, it allows the host to continue booting, but it still doesn't get beyond that, and we get the same message saying the drive's not ready. The problem is we've got no way really of knowing which of the two devices is faulty at the moment, because, well, just because it locks up the host doesn't mean that that's the one that's not working. It's possible that during the startup of the board it's supposed to assert basically the halt signal to stop the host doing anything until it's finished a process, and then it may release the halt. Whereas the other one that's allowing it to boot up might be the one that's faulty because it's not doing what it's supposed to. So we don't at this stage know which of the two is faulty. So what I've done is I've taken out all the custom ICs. There are 6 or 7 custom ICs for this board. You can see them lined up here on the right, and don't really know what they do internally. A few are for serial to parallel and the other ones vice versa. And the rest are described as logic assist ICs or devices. They're custom, especially a custom chipset, and as I said, we don't have any spec sheets for them, don't know what is inside them, so we'll have to try and figure that out as we go. So what I've done is I've taken all them. So what I've done so far is, as I say, I've poked around with a scope. I've removed all the custom chips because they don't actually need to be there to allow the processor to start up and go through the first stages of the boot up for the board. It is kind of a standalone microprocessor system. And using the scope, I found a failing buffer chip. That's the one over here, so I've swapped that, put a socket in there. I've also removed the two SRAM devices. I don't want those getting damaged, but I have refitted one of the custom chips just because I need one of the signals it provides, but all the rest are still removed from the board. So the board's not going to run past a certain point, but it should get to the stage where it's starting up the software. So before I start the fault finding process, I thought it might be interesting just to explain a little bit about the processor on this board. Very unusual processor, very interesting. It's an 8X300, although this board did have an 8X305 when it arrived, and that's behaving differently to the 300 I now have fitted. But I will come back to the 305 in another video once we've tried to establish what's going on with the board. But as I say, I thought it would be good to explain a bit about the processor itself and a bit about the way this board is configured, and it's quite an interesting setup, and if you're not interested in the kind of inner workings of a microprocessor, then you might want to skip this video, but we will get on to some fault finding and hopefully try and figure out what's wrong with this board. Now, as I say, the 8X300 is a very interesting device. It's very powerful for what it does and the speed it runs at. In this board it runs at 8 megahertz, but it has some features that make it run much faster than a device running many times faster. It has a couple of drawbacks in my opinion. One is it doesn't really have an interrupt system, and because of the way it works, that's not much of an issue for a system like this. We'll come back to that later. The second drawback is the sheer size of the device. It's quite a big device, and if you're trying to make a compact board, that might be a bit of an issue for you. However, having said that, it's smaller than the 68000 processors, which had the same spacing for the rows, but obviously has 14 more pins, 64 pin device for the 68000, 50 pin for the 8X300. And you'll get the idea of how big these are when I put them next to a Z80, and you can see that they are substantial devices and do take up a lot of board space. But the advantages you get with this device is it's very flexible for driving hardware systems. Now, rather than look at the datasheet straight away, I thought we'd look at the schematic for this particular board, because it's going to make it fairly easy to explain how the device works. So we'll grab the schematic. These were supplied to me by the owner of the system, and I would say that the documentation that's available for the NCR machine is fantastic. It's fantastic schematics, really well drawn, and also the technical documentation is fairly complete. It's technical explanations, source code for the ROMs, and it really makes it much easier to fault find. It would be very difficult, and I probably wouldn't even bother trying to proceed with this without the documentation. In addition to that, a few people have spent time collating all the information, gathering it together. If you search the internet for the NCR computers, you'll find their websites, and also someone's written a very good disassembler for the 8X300, and it's not quite as simple a task as it might first sound, although the processor doesn't have many instructions. As I go through this explanation, you'll see that the decompiling the code for it is quite a complex task, but he did a very good job. And the disassembled code I'm using, I didn't use the disassembler to create it. This is disassembled code that was created by somebody else, and it is very good. I've just added a little bit of information to the listing, which I'll show you later on. But looking back at the schematic for this board, we've got the processor here, and you'll see it's a bit of an odd arrangement. We've got the address lines coming out only go to its own ROMs. They don't go anywhere else. We'll deal with this line going down here in a minute. So as the device runs, it puts out an address on the address bus that goes around to the ROMs, and the ROMs provide a 16-bit instruction, 16-bit wide instruction for this. And I will go over some of the instruction formats later. And because it's 16 bits, we're using two 8-bit ROMs. In fact, they're PROMs, but they work the same as a ROM, of course, just a bit faster. And that's an important point with this. With this design, speed is everything, and it's designed to run very efficiently. And as part of that, if you follow this bus round, the address bus, we'll go down and we'll find that here there's another ROM. This is exactly the same devices as these, it's just got different code in it that we'll have a look at later. And the way this works is that by adding this extra ROM, we run the device in what's normally referred to as extended microcode mode. So in basic operation, without a device like this, there are 4 control lines coming out of the processor. So we have one that's referred to as SC, that's a command selection line, and that determines whether we're putting an address or data out onto the IV bus, or we're reading data in from the IV bus. The IV is interface vector. For some reason they call it interface vector, but it's a bidirectional 8-bit bus. We've then got a write enable line, and that is used to flag to external devices whether we are writing or reading. Notice here it's not actually connected. And then we've got another line up here labelled RB, that's for write bank, and that goes across in this case to some RAM. And we've got another pin, it's actually not labelled here, but it's LB, left bank, and they really are bank selection lines. So by outputting an address onto the 8-bit bus, the device can access 256 devices, but because it's got 2 of these, it can double that, and so it can actually access up to 512 unique addresses externally. It can do more than that if it uses latches, of course, but that's the way you would normally use it in basic operation. Typically the write bank is used to control some external RAM. In this case we've got some SRAM here. The addressing for this SRAM on this board is controlled through a counter, so we can load the counter from the processor. That will set the address for the SRAM, but also of course through this pair of gates at the top we can also cause the counter to increment, and we'll go over why this is very good for high-speed operation in a few minutes. But the general idea is that this whole circuit acts like a more modern microcontroller. If we go back down to this ROM at the bottom, because we're not connecting the LB, the left bank output, or the write output, but we are using the write bank, when we assert a write bank instruction, again I'll make that clearer hopefully later on, when we assert a write bank instruction we're really referencing the SRAM. If we assert a left bank instruction, the left bank pin's not connected, but what will happen is by using this extended microcontroller ROM we can output different basically different control lines. This just extends the number of control lines we have, and we can output different control lines for each individual instruction that we're running on the processor. So for any instruction that's in the main program ROM we can have an output that's specific to that instruction because we're running the same address bus. So this address increments in step with our main instructions. So the output from this is specific to each individual instruction that the main processor is running. So that obviously it's split into 2 sets of 4 bits. Bit 3 is not used. The first 3 bits are used to control this device. This is a 74LS137, that's an S137. A lot of these are S versions because they have to switch very quickly, and if they don't switch quickly enough the control signals will not keep up with the processor. The complete cycle time for this processor is about 250 nanoseconds in this board, and that includes a 4-phase cycle that's split into 2 main sections, a read and a write. And that's all in one instruction, that's why it's so powerful, but it doesn't mean that all the support circuitry has to keep up. So the first 3 bits are used to select one of these outputs, so it's really a read selection output. We've got these 7 read outputs, and the last one's not used, spare. So by putting a 3-bit binary value on the input and then enabling this device, we can read one of these 7 external devices. They're not all used for reading, by the way. Some are used for other purposes, which we'll come back to in a minute. The upper 4 bits are used for the write control lines. So we have these write control lines here that go to various devices, and because of the way the timing works within the 8X300, when we're writing we have to latch the data of the control lines that are coming out, otherwise they'll be incorrect when the processor's trying to do its thing. Now for this latch it's controlled by bit 7s. So when we put a value on the lower 3 bits, it makes its way out to this device, selects one of the outputs, and the 4th bit is used to actually enable this. So the 4 bits work together. The last bit is just to enable, the first 3 bits are selection, So these two devices allow us to select one of many read operations on the board, and this bottom one allows us to select one of many write operations. So it's very clever, and of course it's high speed. Like I said, the output of this is available as soon as the instruction is loaded. And that's something we'll come back to in a few minutes, because it can get a bit confusing if you're not aware how the internal timing on this works, especially if you're using a logic analyzer. So the plan of attack here is to attach the logic analyzer, as I've done already. We'll start the machine running and we'll see where it gets to, and then we'll compare the addresses on the logic analyzer with the listing and try and figure out why it's not running. So we'll get this started. Okay, I'm going to start the machine up before I arm the analyzer, and the reason for that is when I put the scope onto the processor pins, it appeared that the processor was just running around a very tight loop. I was getting a very short, repetitive looking sequence. I think it's stuck in a tight loop somewhere. So we'll power the machine up. Okay, and now we'll arm the analyzer and see what it captures. The lines I'm looking at, by the way, are the address lines at the top here, the instruction bus, the in-out data, that's the IV bus, the write bank, the command line, the write, select, reset, and the one at the bottom that's labelled probe is currently connected to the left bank pin of the processor. I use this one to move around to investigate various signals. Okay, so we'll arm the analyzer and see what we get. So we have got something. Let's have a look. So the address, incidentally, the pinout and polarity of the signals on this processor is a bit unusual, so if you are going to work with it, I suggest spending some time reading the data sheet, otherwise it can get very confusing. Okay, so we're going through, getting to address, not at the lowest number, 38, 39, 38, 38. So, yeah, sure enough, it's just going around a very tight loop and not doing much else. So the in-out bus is doing something, right bank. Okay, so the control lines seem to be working, but it's stuck in this tight loop. What I'm going to do is go and print off the relevant page from the listing I have, and I'll also decode these three instructions, and then I can explain how the instructions are encoded in a few minutes. But for now I'll go and print off the relevant section, and we'll try and figure out what's going on. Okay, so I've printed off the relevant page in the listing. As I say, I didn't do this disassembly, so thanks to the person that did this, it's extremely useful. And we're stuck in this loop here. All I've done so far is add some comments based on the disassembly and the interpretation of the instructions. I've spent a few minutes going through these three instructions, and also the reset. So it starts here. This is as far as it gets, just these 6 instructions. And I've looked at each of these instructions, put what I think is a comment based on what I believe it's doing, but we're stuck in this loop. And so before we go any further, I'll just explain the configuration, or rather how the instructions are configured and how to interpret them, because it will make more sense as to exactly what's going on here. So looking at the listing, the first instruction we'll look at is the XMIT instruction, and I'll just explain how the instructions are encoded. In the 8X300 there are only really 8 instructions. In fact, each one is more of an instruction group. But they're all encoded in very similar ways across each group, so when you figure out how one instruction works, you can very easily see how the rest works. We'll just do the XMIT one, and I'll explain how that's encoded. So the instruction is at address 0038, and at that address in the ROMs we have CF00. If we look at the listing for the microcode ROM, then at that address, if we follow this across 38, we have a value of 8F. So I've also made a note of that. So this is the instruction in the main program ROMs, and 8F is the value in the microcode ROM. If we put that in binary form, then what we have is this, and we can now check this against the 8x300 datasheet to see what the instruction is actually doing. So this is the relevant page from the manual, and each of the instruction groups has different functions depending on what's in certain fields within the instruction. So the first 3 bits are the opcode, and if we look at what we've got for this instruction, then the first 3 bits, excuse the crudity of this is 6, and if we look, the opcode for XMIT should be 6, so that's correct. Now the next field or fields determine what the instruction is actually doing, and as I said, it varies from in each group of instructions has a similar construct, and what they're doing, whether they're talking to internal registers or through the IV bus, is determined by what's in this field. So if we look at this, the value we're getting, and that's a 5-bit field, and if we look at it in octal, the manual uses octal, then in octal this is 17. And if we look back at the datasheet, we'll see here it says D. If it's 07, it specifies an instruction that's accessing the left bank, that is, the left bank pin will go low on the processor, and if it's a value of 17, then it's right bank, the RB line will go low on the processor, and so we are of course accessing the right bank. And then it will put a value out onto the IV bus, which is the remaining 8 bits, and so the remaining 8 bits, as you can see, is 0. So it's going to put out a value of 0 onto the IV bus and assert the RB line. If we come down and look at the 8F, the microcode value, then that's a value of, in binary, of 1 with 3 zeros. So we'll now see how this works by looking at the schematic. So on the schematic, you can see if RB is asserted, then what we're actually doing is enabling the SRAM. So this instruction is going to enable the SRAM, and it's going to output a value of 0 onto the IV bus, and you can see that bus is what's connected to the in-out pins of the SRAM. And we're also going to get a write enable because of the polarity of the SC line, because the instruction is going to assert this line, and we're going to get a write coming out of here. Now that's not the end of it, because we have our microcode ROM down here, and as I said, the value coming out of this for this particular instruction is 8F. That means that the lower 4 bits are all 1, so if we ignore bit 3 because it's not connected to anything, that means that the value going into this device is going to be 1, 1, 1, and so the value we are selecting here is going to be 7. Now in this case it's spare, so it's not going to do anything. This spare line doesn't go anywhere. So this lower 4 bits doesn't matter, it's not going to do anything. So that just gives us the upper 4 bits, which are 1, 0, 0, 0. So the lower 3 bits are 0. That makes its way through to this device. That'll be 0, 0, 0 at the input. And the upper most significant bit is a 1. And because it's inverted, that means we'll get a low level here that will enable this device. So with 0, 0, 0 on the input and the device enabled, that means we're going to get WR0 going low. And the number in brackets after tells us where this signal goes to. So we have numbers along the bottom and letters up the side. So in this case it's saying it's at D13. If we follow that through, we end up up here. So this line, the WR0, is going to go low. And what this does is it goes through and it toggles the clock line going to the counters. These are all cascaded, so it's this one counter. So in other words, this instruction, single instruction, is going to write a value of 0 into the current address of the SRAM, and then it's going to increment the counters to point to the next address. If we then go back to the listing, we can see that what happens after that is we have this NZT instruction. Now what this is going to do, it's a very similar construct. I won't go through it in a lot of detail. If you want me to go through more of this, then please leave a comment. But what this instruction will do is it will check a particular value coming in on the IV bus, and if that value is not 0, it will branch to 3B, which is, as you can see, down here. But it's not, it's just going around in this tight loop. So because it's not branching, it gets down to the next instruction, which is a jump to 0038, hence it jumps back to the start of this tight loop. So what I believe is going on here is we get to the startup of the code. This is the first bit of code that runs when the processor starts up. It's writing a value of 90H to what's deemed here as Mac control. Look at the schematic. That's this device, and this device is used to control the mode the board is running in. So that's initialized. It then initializes a value that goes to a latch that controls which drive we are talking to. This board will support up to 4 drives, and which head we have selected, and it basically deselects them all. It's just initializing that, nothing's selected. And then it sends a value of 0 to what here is termed RAM address, and that is this counter. So it's basically zeroing this counter, setting the output to 0. So in other words, it's the first address of the SRAM. In fact, it's not the first address of the SRAM. The first 2 bits are hard-coded, so you need to take that into account because the order of these bits is a bit unusual. So just assume that we are loading a value and that it will increment. So we load a value of 0 into the counter, we write a value of 0 to that address in the SRAM, and at the same time we increment the counter. If this input value is, basically if it's 0, then we loop around and we do the same thing again, but remember we've incremented the address. So what this is doing, I believe, is clearing the SRAM. And this RD2 value, if you decode the instruction at this address, then what it's actually doing, so if we look at the schematic, then what's actually happening here is the value for that address that's coming out of the microcode ROM. All it will do is it'll be decoded, and the value there simply lowers the RD2 line. And the RD2 line, if we trace that, goes to C22, so we'll find C22 in our schematic, another page. So C22 is up here, and it's coming to this buffer, so RD2. That goes low, it enables this buffer. This buffer will put its contents onto the IV bus, so this in-out bus is the IV bus. And again, if we look at the value in the instruction, so I've decoded it and checked that what we're looking at here is actually bit 7. So bit 7, so what it's doing is passing this line through the buffer, and it's checking to see if that is actually a value of 0. If it is 0, it stays in that little loop. So in other words, it's waiting for this line to go high. So if we follow this through and find out where it goes to, it's going to C12, and its designation is ROVF. So C12 is back on the first page again, so that's here, and it comes to this point. And this is effectively the nth bit of the counter. So these bits are all used for the address of the SRAM, and this is effectively an overflow bit. So I think what it's doing is just waiting until it's addressed all the SRAM, and then when that last bit overflows, it knows it's finished, and that should then come through this buffer onto the IV bus, and when it carries out this test, when that line is no longer 0, it should cause us to branch to 3B. So I hope that all made sense. If you want me to go over that again in more detail, then leave a comment. But hopefully you kind of got the gist of this. It's quite complicated until you get your head around it, but it's fairly straightforward once you start looking at the instructions. Now it's not actually doing this, is it? It's staying in this loop. So for whatever reason, either the counter isn't counting, or for whatever reason we can't see the last bit of the counter. What we can do now is get the scope out and start looking at what's going on the actual board. So the first thing I'm going to do is, because it's the relevant part to look at, if I can find the right page of the schematic, is we'll check to see, because we know that the correct value is coming out of the ROM. We've got that on the logic analyzer. So the next thing we need to do is look to see if this line is actually going low. So in other words, make sure that the value coming out is being checked. And what we can then do is follow that back through to the counter, see if the counter's not running or if it's not being clocked. It could be we've got a problem up here. I don't think it'll be the buffer. That's the buffer I replaced. That's the one I've replaced down here, unless I've done some damage to the board, which I think it's not likely. I always check the board under a microscope when I take a part out. I'm also very careful when I remove parts, but it's possible. But first thing we'll do is we'll check to make sure this is doing what it's supposed to do. So that's pin 13 of U30. Now unfortunately you're not going to be able to see this because it's obviously covered up in these wires, but hopefully you can see the scope. It's the yellow trace on the scope. I'm going to power the machine up. I need to find U30 on the board, which I have, and then find pin 13. And so I can barely see the device. Just trying to avoid knocking the camera. Okay, so that's working fine. Now the other thing I want to look at before we start suspecting the buffer is another output from here is the WR0 line. So that is the line that's supposed to be toggled when we write to the RAM. So we need to, if you remember when we decoded this instruction, it also toggles that particular pin. So that comes up to here. So if either one of these lines goes low, it creates a clock pulse for the counter. So it's possible that if the counter's not running, we never count up to this value. So that is pin 1 of U11, and that should be toggling. So pin 1, let's try to find U11. So that's this one. We should see. I've got the right pin there. Okay, so there's nothing there, so I'll just make sure it's not a break in the board. That should be pin 15 of U24, so we'll find U24. Look at pin 15. Okay, there's nothing coming out of it, so we'll check the inputs to that device, which is what's coming from the microcode ROM. That's the first one. That's the second one, and that's the third one. So you can see they are all going low as they should do, but we're not getting any output. So I'm suspecting that device is faulty. So that's the input. So we'll check the output again. So it should be, just double checking, that should be pin 15. And there is nothing there. So, okay, well that device is clearly not working. We'll just actually check to make sure it's getting an enable signal, which comes from the SC pin. Okay, so that's permanently enabled in that mode. So, okay, so clearly we're not getting operation of that counter incrementing. It's not getting a clock. Okay, so this video is getting a bit long, so what I'll do is I'll find a replacement device, I'll swap the device, and in the next video we'll see if the code gets any further. Before we finish the video, actually, I just want to show you one more thing on the analyzer, just to make sure that if you have been looking at the analyzer trace, or if you go back and look at it, it might be a bit confusing. So I'll just move the camera. So when we look at the logic analyzer output, it looks like I've made a mistake. We decoded the instruction at address 38 as being a right bank instruction. It was going to access the right bank, which means it would lower the right bank line, which is this yellow line. But you can see that it doesn't appear to be lowering that line until the next instruction at address 39. Now, it's not a mistake, it's because of the way the internal timing works on the ATEX300. And if we look at the relevant page in the datasheet, you probably can't read this, but the processor operates on a 4-phase system. It's fed with an external clock, in this case it's an 8 MHz crystal, and it uses each half phase of the clock cycle for each one of the 4 phases, so it's 2 full clock cycles for each instruction. What it actually does is it loads the instruction in the first half of the first clock cycle, and to make sure that data is ready, it actually outputs the address for the next instruction in the 3rd phase of this cycle. So this is the point at which the data is going to change for the next instruction. So it does that ahead of time. It's already decoded it, so it doesn't need the input anymore, so it gives the PROMs or the ROMs plenty of time to output their data ready for when it starts the next instruction. But because it's loading, it's outputting the address at this point, remember that the address lines are connected directly to the ROMs, and the ROMs are permanently enabled, so they will output the data or the instruction for the next instruction before the currently executing one is finished. And that's why these appear to be out of step, so just bear that in mind if you're using a logic analyzer. Now, if you're doing a lot of work like this, it would be easier to take the crystal out of the board and feed the processor with an external 8 MHz clock and use that to control the state input clock of the analyzer. So just bear that in mind if you're trying to follow along and wondering why these don't seem to tie up with what I'm saying. Okay, so in the next video I'll have replaced that what we think is a faulty IC, and we'll see if the code will go any further.